In the last video we saw the second order linear differential equation with constant coefficients. It was also a homogeneous differential equation because 0 is on the right hand side. We found that the auxiliary equation associated with it is just ak squared plus bk plus c equals naught. And the solutions to this quadratic equation can be plugged into this function here to give us solutions of this differential equation. Of course, we know that when we solve a quadratic equation, the nature of the roots depends on the coefficients a, b and c. So here's the formula for getting the roots of a quadratic equation. So we're really interested in the value of this expression here. This is called a discriminant. It discriminates between the types of numbers that k can be. If b squared minus 4ac is greater than 0, or we can write that as b squared greater than 4ac, then we will have two results for the square root. The plus or minus sign gives us two results if this is greater than 0. So we'll have two distinct values for k. And of course the roots will be real because we're getting the square root of a positive number. B squared minus 4ac is positive. So we will have two independent solutions. Let's say one of the values of this is k1 and the other value is k2. We know that e to the k1x and e to the k2x are linearly independent. One of them is not a multiple of the other, so we can get a linear combination of them to get a more general solution to the differential equation. So a and b are any constants. So that's the situation when the auxiliary equation has distinct roots k1 and k2. Now what if b squared equals 4ac? So let's see that here. If b squared equals 4ac, well, that's the same thing as saying that b squared minus 4ac equals naught. So here we'll have the square root of naught. So we'll have plus or minus 0. Well, that's just 0. So we just have one solution. We just have one value for k. It'll be minus b plus or minus 0 over 2a. So whether we take plus 0 or minus 0, we just get one solution. The solution will actually be given by minus b over 2a. Then k will actually equal minus b over 2a. Now, in this situation, we only have one independent solution, so special treatment is required in that situation, so we'll get back to that. Now, what about if b squared is less than 4ac? Well, that's the same thing as saying that b squared minus 4ac is negative. So we'll be getting the square root of a negative number, so we're into complex numbers. We'll have two complex solutions in that case. So let's take some examples. Here's a constant coefficient differential equation. The auxiliary equation that goes with it is k squared plus 3k minus 10 equals 0. So we just have to solve this. We don't have to show the plugging in of e to the kx anymore because we know we are going to end up with this auxiliary equation whose solutions gives us the values of k for the functions that solve this differential equation. So we just solve this quadratic and we get two solutions, 2 and minus 5, two distinct solutions. So b squared minus 4ac is positive for this. Or we can say that b squared is greater than 4ac for this differential equation. Now let's look at this one here. What's the auxiliary equation? Well, a is 1, the coefficient of the second derivative. B, the coefficient of the first derivative, is 0. And c is 4. So we get 1k squared plus 4 equals naught. This is what we'll get if we plug in y equals e to the kx into this. And then when we factorize e to the kx out, the other factor will be k squared plus 4. Set that equal to naught, and because we've naught on the right hand side, of course. And this is a very simple quadratic to solve because we don't have any k term. We don't have to use the formula. We can just bring the 4 over and take the square root. Now we're getting the square root of a negative number, so k is a complex number. The square root of 4 is 2, but the square root of minus 1 is written I, and we have two possibilities. We have the positive or negative square root. So we have two complex roots. So we plug plus 2y in for k, and then we plug minus 2y in for k to get our two solutions. Again, these are independent. You know, if we take one of them and divide by the other one, we'll get a function of x. We won't get a constant. So from our previous results, we can get a linear combination of these two solutions. So there's nothing really new here. We just have complex numbers for k. What we can do, however, is use Euler's relation to rewrite e to the 2ix like this here. So we take cos of 2x as the coefficient of I, and then we've I sine of 2x. And we do the same for e to the minus 2ix. We get the cos of minus 2x. Now the cos of a negative angle is the same as the cos of the positive angle. Then we have the sine of minus 2x. Well, that's the same as minus sine 2x. So as a reminder, we're using these results here, and we're applying it to minus 2x, cos minus 2x plus I sine minus 2x. So we now take a linear combination of these two solutions. Notice that we have a cos 2x plus b cos 2x. That can be written as a plus b times cos 2x. Now since a and b are arbitrary constants, a plus b is an arbitrary constant. So why not call it something else? Just call it c. It's just some number. The sum of two arbitrary numbers is some arbitrary number, which we will call c. We don't call it a or b, of course. And as for the imaginary part, we have a sine 2xi minus b sine 2xi. So we can factorize sine 2x out. So we have ai minus bi multiplied by sine 2x. Well, a and b are arbitrary constants. ai is a constant. So is bi. A and b could be imaginary actually. They don't have to be real numbers. So we combine these together and call it d. So d in general is probably an imaginary number. It's a complex number, but it's still a constant. So we can write our solution like this. You can check this then by just plugging it in here. You will see that it doesn't matter what c and d are. They can be any numbers, real or imaginary. It will all work out to 0. Right, let's take a general case. Here's our second order linear differential equation with constant coefficients. It's homogeneous, 0 on the right hand side. Let's suppose that the roots of the auxiliary equation are complex, and we denote them by k1 and k2. By the way, if the roots of a quadratic equation are complex, then one root is the conjugate of the other root. We want to show that the general solution of the differential equation is given by this here. So first of all, we have to get the auxiliary equation. Now you can go through this from first principles by using the trial solution e to the kx. We know that that satisfies this homogeneous differential equation. And of course, we know that if we do that from the previous video, that we will get out the auxiliary equation as ak squared plus bk plus c. So we don't have to go through all that. We can just write down the auxiliary equation just by noting the coefficients a, b and c. So if the roots are complex, then beta is not 0. Otherwise we have real roots, although real roots are actually complex numbers, but we're talking about non-real roots here. So we need that beta be non-zero so that we have two distinct solutions to this equation. So we will have two independent solutions to the differential equation when we plug in for k. So we will have e to the alpha plus beta ix as one solution, and e to the alpha minus beta ix as the second solution, and these are linearly independent. Because if we divide e to the alpha plus beta ix by e to the alpha minus beta ix, we get a function of x. We don't get a constant. Okay, so anyway, we take a linear combination of these as we've seen before, and now we can actually rewrite this. We can see that e to the alpha x is a common factor. We can first of all factor each of these exponential terms. We can write this one here as e to the alpha x times e to the beta ix. Just add the powers to get back to this. Similarly over here, we can write it like this. So e to the alpha x is a common factor that can be pulled outside. Next we apply Euler's relations. So we have e to the beta x times I. So the coefficient of I here is beta x, so we get the cos of beta x and the sine of beta x. We have cos beta x plus I sine beta x equals e to the beta xi. Similarly over here, e to the minus beta xi is cos minus beta x plus I sine minus beta x. But the cos of minus beta x is just the cos of plus beta x, and the sine of minus beta x is minus sine beta x. Factorize cos beta x out of c and d, so we have c plus d cos beta x. C plus d is just an arbitrary constant, since both c and d are arbitrary constants. And we can factorize sine beta x out, so we get ci minus di. That's an arbitrary constant, so we can rename them. So we can call c plus d a, or anything other than c and d, of course, and we can call ci minus di b, and we get our general solution. So here it is highlighted. Remember, we call the general solution of the homogeneous differential equation the complementary function, because later on we will be dealing with non-homogeneous differential equations where the right hand side is not 0. So here's an example. Well, the auxiliary equation is 1k squared plus 2k plus 4 equals 0. Turns out that this has complex roots. So let's just go through those. Minus b plus or minus the square root of b squared minus 4ac. That's 2 squared minus 4 by 1 by 4. 2 squared is 4, minus 16 is minus 12, and this is divided by 2 times a, where a is 1. So we have the square root of a negative number. B squared minus 4ac is negative, so we're going to have complex roots. So we have minus 2 plus or minus the square root of 12 times the square root of minus 1. So we can factorize it like that. Write I for the square root of minus 1. Now 12 can be factorized as 3 times 4. So we've root 3 times root 4, or root 3 by 2, 2 root 3. So we end up getting minus 1 plus or minus 1 root 3i. So we have two solutions. So one of them is minus 1 plus root 3i, and the other one is minus 1 minus root 3i. Two distinct solutions. One solution is the complex conjugate of the other. So now we can just write down the solution using this formula here. So alpha plus beta I is one solution, and the conjugate is the other solution. So we can see that alpha is minus 1, the real part of the complex number. Beta is just the magnitude of the imaginary part. It's root 3. So we plug minus 1 in for alpha and root 3 in for beta, and we get our general solution.